Slide 1. Welcome to Networking and Health Information Exchange Supporting Standards for EHR Application. This is Lecture B. This component, Networking and Health Information Exchange, addresses what is required to accomplish networking across and among disparate organizations who have heterogeneous systems. Unit 7 covers Supporting Standards for EHR Application and consists of 4 lectures. Over these 4 lectures, we will talk about the additional standards that are available to support interoperability across different applications that relate to or are interactive with the electronic health record. In Lecture B, we will look at several guideline standards, but will focus on the HL7 Guideline Interchange Format, GLIF, standard, and the ASTM Guideline Elements Model, GEM, standard. We also will have a brief introduction to GELLO, an object-oriented expression language for clinical decision support. The discussion on GLIF is included only for illustrative purposes. It is in very limited use, and it is being replaced by guidelines written in GELLO. Slide 2. The objectives for this unit, supporting standards for EHR application, are to understand the Clinical Decision Support Standard, Arden Syntax. Understand standards for clinical guidelines. Understand Object-Oriented Expression Language for Clinical Decision Support, GELLO. Understand the Clinical Decision Support Standard info button. Understand Disease Management, and understand other clinical decision support applications. Slide 3. Additional objectives for this unit, supporting standards for EHR application, are to understand other standards that help to support networking and reporting requirements as well as functionality to optimize the connectivity among heterogeneous systems deployed within a single enterprise. Understand single sign-on standards and the HL7 Clinical Context Object Workgroup, CCOW standard. Understand regulatory standards, and understand issues relating to person identifiers, master patient indices, and record locator services. Slide 4. Clinical practice guidelines serve to reduce inappropriate variations in practice, to improve patient safety, to improve healthcare, and to reduce costs. Although the importance of guidelines is well accepted, the use of guidelines is still limited, and the conformance in use, typically less than 50%. Guidelines are typically integrated into the workflow and involve direct, real-time interaction. Guidelines may also provide automated reminders and alerts. Guidelines support order entry and may be an asset to the consistent capture of data. We are interested in standards for guidelines in order to share computer interpretable guidelines. Guidelines deliver patient-specific recommendations. They may be integrated with EHRs to provide, among other things, automated reminders and alerts, to do decision support and task management, to do order entry appropriateness, referral criteria, and to do background monitoring, care plans, and quality review. Slide 5. Benefits of guidelines include the ability to provide automatic decision support that can be applied to individual patients and to perform retrospective analysis to verify that patients were treated appropriately. Guidelines guide simulations and aid human visualization through interactive dynamic displays of guideline pathways. Guidelines allow one to focus on relevant sections of a flowchart. Guidelines may be applied to individual patients, integrated clinical data, and knowledge to guide the encounter. Physicians are often biased by recent experiences. Guidelines support consistency. Guidelines also reveal the logic behind decision-making and can provide a visualization of that logic. Guidelines capture the experience of experts and bring equality to patient care. Slide 6. Sharing guidelines invokes many challenges. Local adaptation of guidelines, including availability of resources and expertise, local workflow issues, and practice preferences. Integration with local information systems by matching patient data from EHR to GL, and by matching recommendations in guidelines to actions in order entry systems. Dissemination formats. Perhaps the biggest barrier to the use of guidelines is the concept of cookbook medicine. Guidelines only guide the provider in what is common practice. Many guidelines are incomplete and don't fit the individual patient who the provider is seeing. Most guidelines are adapted to the local environment because of the preference of the providers, local cultures, and the nature of the patient seen. Guidelines should be interfaced with the EHR to use existing data. Guideline representation is critical for both computer implementation as well as the ability for sharing clinical guidelines. Slide 7. The potential for the use of guidelines is huge. Guidelines are part of meaningful use. If guidelines are produced by domain experts, the length of time from research to routine use can be significantly shortened. Guidelines must be shared in a technology-neutral format that they can run on different platforms and systems. Guidelines should be implemented using the service-oriented architecture. Each guideline becomes an encapsulated, enclosed component with a defined set of input parameters and delivering a defined set of outputs. The development of guidelines is also enhanced by tools to support authoring, validation, and maintenance. Slide 8. Guidelines need to be expressive to cover all the nuances of patient care and decision-making. For computer interpretation, the guidelines must be structured and include definitions, data requirements, recommendations and actions, and logical, decision-making algorithms. Guidelines are based on an expressive decision model. Inputs and outputs must be clear in specifying the work to be accomplished. Actions must be expressive, complete, and clear. Data must be interpreted correctly. Guidelines are also used to generate alerts and reminders. Slide 9. Guidelines must show the underlying logic when queried. This explanation is most often expressed as a block diagram or flow diagram showing data requirements and decision points. Guidelines must be able to handle the complexity of a clinical event and must support the variations in patients and settings. Guidelines must support various actions. When a provider is not compliant with a guideline, the system should request the reason. For example, a foot exam for a diabetic patient may not be conducted because of a request from the patient. That fact should be noted so a follow-up action can be initiated. Guidelines must include the authoritative source for the decision logic, a literature reference, the guideline expert source, or other authority. Slide 10. The introduction of guidelines into the workflow is often awkward. For example, if a patient qualified for the use of 3 guidelines, each guideline would be presented to the provider consecutively. If the same piece of data were required in each guideline, it would be asked 3 times. If data is available from the EHR, it should be automatically added and not require the provider to re-enter the data. An even better approach would be to take the guideline requirements and merge them into the order entry approach. One challenge in the sharing of guidelines is the matching of data elements identified in the shared guideline and the local setting. Slide 11. One workable approach for the use of guidelines in mapping guideline data requirements to the local setting is through the use of a virtual medical record, VMR. In this case, data is extracted from the local system and placed in a virtual record in the data position defined by the guideline. The guideline can now function interoperably with any system. This process divorces the data requirements and the logic from the local environment. The output can go through a similar procedure where the output from the guideline is mapped into the local terminology. There is, however, the risk of the loss of information. HL7 has a group developing standards for this approach, VMR. The success of guideline use depends on how effectively the use of the guideline is integrated into the workflow. If the guideline is perceived to take additional time or require a disruptive action on the part of the provider, the guideline is likely to be unused. Slide 12. The National Guideline Clearinghouse, NGC, sponsored by AHRQ, makes available a number of guidelines to providers at no cost. As of February 20, 2012, the NGC contained 2,319 individual guidelines. Guidelines are indexed by a number of parameters, including category, disease, creating group, and others. This website is one of the best resources for obtaining clinical guidelines. Slide 13. This slide shows a list of common guideline representation models. We will discuss the first three in detail: Arden Syntax, GLIF, and GEM. Dilemma, spelled D-I-L-E-M-M-A, represents guidelines as a set of protocols within which actions are encoded. EON, spelled E-O-N, uses activities, actions, and provides advice as a patient scenario and discusses activity states. Proforma uses an enquiry action for information collection. ASBRU, spelled A-S-B-R-U, uses a similar approach to dilemma. Guide, spelled G-U-I-D-E, has a weight action as its knowledge representation is in the form of Petri nets. Prodigy, spelled P-R-O-D-I-G-Y, uses a similar approach to EON. EON and GLIF use decision steps. Proforma, Guide, and Prodigy use decisions. Arden uses logic slots. Dilemma uses state transition. And ASBRU uses condition preference as the decision-making process. However, none of these guideline executable models have come into widespread use. Slide 14. One of the most popular representation models for guidelines is GLIF, developed by Dr. Bob Greens and colleagues. GLIF is a format for sharing clinical guidelines independent of platforms and systems. It is based on an object-oriented logical model of concepts and uses XML syntax. It is an executable model. GLIF serves only as a model today. Further development has been discontinued. Attempts to promote GLIF as a guideline executable standard failed because of the inability to get agreement among several models. The HL7 Clinical Decision Support Workgroup decided to focus on GL modeling elements, such as the expression language GELLO. The data model, which is the origin of the Virtual Medical Record (VMR) project, and possibly a workflow description formalism, which never generated a project, that all GL models could use, rather than the GL model itself. There was also a lot of time spent on narrative GL markup models like GEM, but none of these were expected to lead to GL execution models. Also, many of the CDS-WG came to recognize that it would be very rare indeed that a GL execution model would ever be used in practice, except for strict clinical protocol situations, but rather that a GL would be executed in terms of components like single-step rules, order sets, etc. That is, it would be decomposed rather than run as is. Because of all these factors, interest in an executable GL model waned. It seems unlikely that this activity will be sustained. This model is included in the discussion, however, to illustrate the kinds of things these standards must address. Slide 15. The GLIF model, similar to Arden Syntax, identifies the title of the guideline and the author. Also similar to Arden Syntax, the model includes decision steps, action steps, branch steps, synchronization steps, and a patient sleep step. Slide 16. By now, what these terms mean should be obvious. An action step might be to order a lab test or to prescribe a medication. A decision step is a conditional or decision point in which the flow branches depending on the result of a condition. If the patient has pain, then action. Branch steps permit changing flow depending on decision logic. Synchronization steps permit arresting action until a step is complete. For example, the entry of a result of a lab test and patient state sleep provides for a continuation of the guidelines over a period of time, including multiple encounters. Patient state sleep characterizes the patient's clinical state. Slide 17. GLIF provides 3 representation states. The first is from the perspective of the author or viewer of the guideline, the conceptual flow of decisions and actions. This view meets the condition of explaining the logic of the guideline and aids in human understanding. The second is the abstract machine representation, the computer executable form in which correctness can be analyzed. The third level is the integration of the guideline into the workflow environment. Slide 18. The abstract machine representation is similar to that of the Arden syntax. The logical expressions and actions are based on defined steps based on medical oncology. The guideline defines values, constraints, and timelines. The guideline can be interpreted and analyzed for correctness. Tools provide syntax checking, type, and range checking of data elements. Slide 19. The Guideline Elements Model, or GEM, was developed at Yale University Center for Medical Informatics by Dr. Rick Schiffman. It is now an ASTM standard and has continued to be developed. It uses a hierarchical data structure to organize the heterogeneous information contained in practice guidelines and uses an XML editor designed specifically for guideline markup. The XML editor is cleverly named the Gem Cutter. Slide 20. This slide shows the hierarchical structure of GEM. Logically, it uses defined data elements, conditional logic, decision variables, and logical constructs with resulting actions. The overall structure defines data terms and decision algorithms. Details of GEM are available from ASTM, including data element definitions used in the guidelines, available as a PDF. GEM is defined as a document type definition, DTD. A document type definition defines the legal building blocks of an XML document. It defines the document structure with a list of legal elements and attributes. A DTD can be declared inline, inside of an XML document, or as an external reference. Slide 21. GELLO is a class-based, object-oriented OO language that is built on existing standards. GELLO expression language is based on the Object Constraint Language, OCL, developed by the Object Management Group. Relevant components of OCL have been selected and integrated into GELLO to provide a suitable framework for manipulation of clinical data for decision support in healthcare. The GELLO language can be used to build up expressions to extract and manipulate data from medical records, construct decision criteria by building up expressions to reason about particular data features or values. These criteria can be used in decision support knowledge bases, such as those designed to provide alerts and reminders, guidelines, or other decision rules. Create expressions, formulae, etc. for other applications. Use cases for GELLO include medical experts, researchers, home economists, epidemiologists, knowledge engineers, and programmers. It is the language that permits the application of knowledge to data of use in multiple clinical applications, including clinical guidelines, template constraints, alerts, and recommendations. Slide 22. The syntax of the GELLO language can be used with any object-oriented data model. In the context of clinical decision support, such an OO data model can be any refined message information model RMIM view of the HL7 RIM. An example of an RMIM view of the HL7 RIM is the virtual medical record. The VMR functions as a limited view of the multiple classes in the HL7 RIM, showing only those classes relevant to the clinical decision support application. A major problem to sharing clinical knowledge is lack of a common format for data encoding and manipulation. Based on the premise that GELLO can fully provide expression support for any properly defined view of the HL7 RIM, the development of GELLO is independent of any particular specification of an OO data model. It is thus only necessary when producing a set of decision support applications using GELLO to specify the particular object-oriented model used. Thus, GELLO addresses many of the problems of the lack of semantic interoperability as a result of data structures. GELLO can accommodate any properly defined OO data model. Slide 23. GELLO products are targeted to clinicians who need to use expression language for sharing and manipulating knowledge in medical context. GELLO is becoming increasingly popular. The reasons include that GELLO is a declarative language, extensible, vendor-independent, platform-independent, object-oriented and compatible with VMR, easy to read and write, side-effect-free, and flexible. GELLO is easy to use, read, and write. Slide 24. This slide shows the relationship of GELLO to other key components in decision support. GELLO serves as a vehicle to tie together the different areas, including Arden Syntax and GLIF, representing guidelines and sequential knowledge, RIM, representing the information model and coupling ontology, and other data storages and knowledge databases. The advantage of GELLO is that it can accommodate existing work, including the Arden Syntax and GLIF, that represent sequential knowledge. GELLO uses the HL7 RIM as a link to interoperability, and finally, GELLO can provide a link to many of the other knowledge representation models mentioned earlier in this lecture. Slide 25. GELLO expressions are text strings satisfying GELLO language specifications. The result is an expression that can be evaluated for actions. GELLO accommodates temporal actions. GELLO uses the basic data types, Boolean, real, integer, and string. It supports a wide range of mathematical operators, including trig functions, logical comparator operators, math operations, and string operators. It provides considerable power in interacting with data elements. GELLO syntax is a context-free grammar consisting of a number of productions. Each production is formed by two parts, the left-hand side consisting of a non-terminal symbol and a right-hand side formed by a sequence of one or more non-terminal and terminal symbols. GELLO uses a Backus-Naur form, BNF, syntax. GELLO examples of expressions are calcium.notEmpty and phosphate.notEmpty, renal_failure and calcium_phosphate_product greater than threshold_for_ osteodystrophy. GELLO also includes temporal operators. Slide 26. This example looks for the presence of azotemia observation within the last 3 months. Assumptions. 1. The data model has as code a generic term such as SNOMED finding 246188002, and the value slot has the code for azotemia. 2. For a diagnosis such as azotemia, the effective time is the time interval during which the disease is thought to be present. 3. A point-in-time.now function returns the current time. The specific GELLO representation for this logic is shown on this slide. Slide 27. This concludes Lecture B of Supporting Standards for EHR Application. This lecture has discussed guideline representation models. The future of such work is likely to be based on GELLO. Guidelines themselves are very important. Use of guidelines should increase significantly with pressure from meaningful use. IOM released a study on clinical guidelines in 2011.